Let's go over the warm-up here. So, Itai, want to take the first one for us here? Talk to me about how you do it, not just what you get.
Okay, I'm not entirely bothered, but I think that you just kind of multiply it 20 times, so like 9 tenths to 100 pounds.
And what do you get? Did you actually compute it?
No, not yet. I'm still not sure if that's the right process.
I think that's an okay idea. They're independent.
1, 2, 1, 5.
What is it?
Good job, Itai.
About 0.1216.
Point, what is it?
1216.
1216. Okay. Sweet. What about B? Take it for us.
Wait, it was right.
Yeah, do you have it? Well, I don't know. Well, maybe we do. Right, it's just basically 0, right? Is the point. All right, so maybe we won't write out what that is, but Josh, can you take the part C? How would you get that? Or at least get us started. What's your first thought on it, at least?
Just setting up like C of x equals 17 and then with the...
Can you say that again? Sorry.
C of x equals 17 is going to be 17 heads.
Okay.
But all percent.
Well, I'm just thinking if we take a similar approach to what we just did doing, maybe we can come in at it. Can you help us, Sarah?
Can I put a friend?
Well, you are the friend.
I don't know.
It's like something to 17 power or something.
Well, yeah, I think we need something to the 17th power, namely what? By the way, this is a ridiculous coin. I love it. Okay. But now exactly 17 heads implies something else too. That there will be exactly 3 tails. So would you like to multiply by anything else while we're in the neighborhood? Huh? Yeah, I think we maybe need that too. And so I think there's a lot to like about this calculation. Can someone say why that can't possibly be it though, fully? What assumption is being made here? Go ahead, Francis.
Aren't there many ways that you could flip it? You could start off with 3 tails.
Yeah, there's only one way to do these first two, so we didn't have to think about this. But keep going.
Yeah, but there's multiple different ways you can have exactly 17 heads.
So this assumes that like it's the 17 heads followed by 3 tails or something like that, and that's a wrong assumption. You could be lots of different ways, Francis says, to have this happen. And now we just need to say exactly how many ways that could happen. How many ways are there from 20 possible flips to choose? Go ahead, Nick.
Is it just 2217?
Why is it 2217?
Because like you have 17, you're choosing 17 things from a total sample space of 20.
Yeah, there's 20 flips that are going to happen, and the selection process is us asking, we need to select 17 of those to be heads. Or, equivalently, we need to, from 20 different flips that we're going to make, we need to select 3 of them to be tails. Those you mean, of course we don't understand those to be the same thing. The other way we could think about it is to think, okay, well, H, T, H, T, T, H. You could have that, for example, or any arrangement of that word, right? And how many arrangements of that word are there? Well, it's 20 factorial over (17 factorial), 3 factorial. Oh, okay, 2217. So there are a couple ways to conceptualize the same counting problem here. Okay, so we're good on that. I hope you all see this is something that's so critical for us to see. Why 2217? So let's pause there. If anyone needs to say more, we can describe it yet another way maybe. I don't know. I want to make sure you're really clear on why it's not sufficient to just have 0.9 to the 17, 0.1 to the third.
Or just another thing, you do the inverse and have it be 22 3 as well.
Absolutely. All right, now someone want to take us through D?
I was going to ask a question.
Yeah, go ahead.
So does order matter in this situation for C?
I mean, it can be, I mean, it's just one coin we're flipping, and so I'm not sure what you mean. It actually doesn't matter whether we're doing it in succession or whether we like throw 20 coins at once.
Like the order of the result, the order of the outcome.
Yeah, it doesn't matter, and that's why we need to multiply by 2217, right? That's exactly why we have to multiply by it, is because if you're not multiplying it, then you're assuming that it came in a particular order, and we want to include all such orderings.
Okay.
Yeah.
But how does that impact probability?
No.
How does that impact?
So we need to add the probability of it happening in this way, which is that. That's the probability of this occurring.
Oh, just so that it
Plus
encompasses-
the probability of this occurring with the t, you know, like plus all of the different ways that we could have written this out and have it qualify. So,
Oh, I get it.
all right. So someone walk us through this somewhat terrible calculation.
You don't need to multiply.
It's a little bit messy. It's what needs to be done. Who would you like to hear from? Aiden or Katie?
No, I already spoke.
All right, Katie is who I'm hearing. Go ahead, Katie. Aiden, don't take it personally. Also, just check on what she's saying. Make sure it's right, okay? You can be the referee.
So it's just 2217 times 0.9 and then 0.1 to the third.
That sounds familiar.
And then plus
Oh, there's more. Okay.
18 times 0.9 to 18.
And let's just stop there for a second. Does everyone see where she's going with this? Maybe you could even
I do get it.
complete this, what she's saying. She's not done, but do you see where she's going with this?
Yes.
Aiden, how'd she do?
That's what I did, so assuming I did well, then she did well. But I mean, I always do well.
Our destinies are intertwined, though, aren't they? Okay. Yes. So let's someone else continue her work, just to prove that you know what she's doing. Go ahead, Chris.
I want to.
2219 times 0.9 to the 19 times 0.1.
And then the last one, you could just say,
It's just 22. It's just 0.9.
yeah, and actually this calculation is made a little better by the fact that we've already done some of these in the warm-up, right? A and C are both contained in this sum, aren't they? So that's cool. And as we do this, this does seem very familiar, doesn't it? Doesn't it seem very familiar?
Oh, this is.
When was the last time we said 20 choose something times this thing to a power plus this thing to a power, that powers add up to this? And this feels like, say it again?
Binomial theorem.
Yeah, this feels like the binomial theorem. This feels like binomial expansion, doesn't it? All you have to do is replace 0.9 and 0.1 by x and y or something. And this would be the expansion for x plus y to the 20th, right? Powers that add to 20. Binomial coefficients. It's all there, friends. Now, this is not the whole expansion. This is just the last few terms of that expansion. But you can imagine the other part of it maybe lives over here and is not visible to us. Whatever this comes out to is our answer, though. Okay. Keep that stored away in your heart for a second. Are there any questions on the homework before we move smartly along?
I was just wondering if the expected value on the calculator rounds, does it round the expected value thing? If you can
It
expect,
eventually does. I mean, but it'll round it at like the ninth decimal place.
so like on a test, if we have to calculate expected value, is it okay if it's like we do exactly what the calculator says with the rounder thing?
If you don't know that it's exact, then no. I mean, you should round to 3 sig unless it says otherwise on the question.
Okay.
And if you know it's exact, like it terminates after 3 or 4 decimal places, then it's exact. You could write the whole thing down.
Okay.
All right. Everything else was okay? Yeah, like I said, you're probably feeling okay about it, given the fact that I said explicitly on Friday that you didn't have to calculate it by hand. You could just use your calculator. Hopefully you're feeling good about that. And of course the answer key will be online for you to check. Well, my claim to you is if you truly understand the warm-up today, then there's not much to teach in the class today, but we will introduce something called, as some of you who have done this kind of calculation before knew that I was foreshadowing. We are going to cover our last lesson of this unit on this kind of probability. Binomial probability is what it's called, and you can already feel what kind of problems we're going to do. It's just the warm-up, basically. We're just going to like come out and say that more clearly that this feels like binomial expansion. That's all. We're just going to put a little bit of a better name to it. So, in fact, the first problem we're going to do feels very similar. We got to stop and think about what is the hallmark of a problem such as this was in the warm-up? Well, here are the things we're looking for. We're looking for independent trials, and by now you, I think, even have a very good technical understanding of what we mean by independent. We mean that when you flip the coin and then you flip it again, the previous outcome didn't affect the current probabilities of the new outcome, right? Which is, of course, the thing we always assume for coins, or for most other, kind of games of chance like this, right? Certainly rolling a die isn't affected by doesn't have a memory. Right, Chad? You mind? The other thing that we're looking for is maybe just like normal, two outcomes, heads and tails. Or in the factory example we're about to do, failure or a defective versus working. Right? Two different outcomes with two probabilities that fill up the distribution. And we'll call those probabilities here P and Q, but just know that P plus Q is 1. Okay? Of course that has to be the case. I'm naming them just for the sake of the discussion, and I'm putting them in quotes. I'm naming them like success and failure, with probabilities of those two things happening. But just know that like success is in quotes because success could mean like, oh yay, we got a defective widget. Okay, well that's not really success in like a moral sense. It's just like we're just naming them. Okay, I just want to make sure you're clear that success doesn't mean like good necessarily or something. In the homework, I think there's like a airplane engine failure question or something. Like that's not like success in a normal sense. It's just having success with respect to that question in terms of calculating successfully what we sought. And then this is the crux of what we just observed in the warm-up in the last problem, right? Right here. P plus Q to the n. Now I want you to think about what would happen if you were to expand, for example, in the warm-up, 0.9 plus 0.1 to the n, to the 20th, I guess, if we're doing the warm-up, to the 20th, right? How would that expansion feel? Now, I know some of you are tempted right away to be like, well, of course you could just add those first. But let's not, and let's multiply it out and actually do the entire binomial expansion. Wouldn't you get, as the last part of that expansion, what we had on part D of the warm-up? That's all we're saying. In fact, consider the whole expansion. Any one of the terms in the expansion, say we're looking for, oh, I don't know, say n is 17, right? Excuse me, not n, but like, say we're looking for the 17 heads or something like that. Well, that will be, you can go to that term and find, and that term, if you evaluate it, will give you that probability. And of course, all the probabilities add up to 1, don't they? But you knew that beforehand, because the first thing you wanted to do is like not expand this. What was the thing you wanted to do? Well, you wanted to say this was 1, right? So of course this equals 1. You thought of that before we even thought of expanding it. You knew it was 1. So this expansion, of course, if you list it all out, does in the end equal 1, but that's not the point of this. It's not to be like, what does it all equal? Well, of course it equals 1. The point is we might want to look at some piece of it that gives a certain probability of something happening. So, I don't know, just let's give this a try here. We need to identify what n is, or what the number of trials is total in this example, and the probability of success, I guess, is. But this is kind of the hallmark of a, let's pretend they're like an infinite number of widgets. This is kind of what we're looking for something to be a binomial probability. We're looking for independent probabilities, 2 outcomes, repeated over and over again. So, in fact, sometimes people write X is distributed binomial NP. Excuse me. Got carried away here. You'll see people sometimes write this. I don't know that they do this in. So for this, we've got a binomial random variable, call it X. with how many are we pulling off? 150. And P, our probability of a defective widget, is 0.008. Careful with the decimal, please. 0.008. Yeah, just mind your P's and Q's. So what are we seeking here? We're seeking the probability that our random variable x is exactly 3. And this is done just like our C, I guess, right, on the warm-up today. So who will take that for us? Go ahead. Good. Good. And then someone out there maybe can also give us the value of that. Say it again. So about 8.7% chance of this happening, that you would get exactly 3 widgets defective off the line. Now, yeah, so I think that's, I don't know, it seems actually somewhat high. 8% chance of that happening. Yeah, so I want to make sure we're emphasizing here that we really are dealing with a random variable here. Probability of x equals 3 is just one of many things we could outcomes we could ask about. To ask about the probability of x equals 0, all the way up to the probability of x equals 150, right? So you can imagine, even if you're into writing out PDFs, you could write out a table like we've so often recently been giving you. The random variable would have the outcome 0 all the way up to 150. That'd be 151 items in our table. You could associate a probability with each one. In this box where x is the random variable is 3, you put this, right? And if you filled all the probabilities out, they'd of course add up to 1. You know, you have a sense. I just want to make sure you have a sense of the big picture here. This is a random variable, and this is a distribution we're thinking about here. Okay, I want to have you have full vision of the whole distribution, which means we can ask questions like last night: what's the expected value? What's the variance of this random variable x? And the expected value for a binomial random variable is very intuitive. So let's ask that right now, on this example right now. What do you think? Forget you heard anything about binomial probability today, just for a second. If I just told you, hey, tomorrow I'm going to pull 150 widgets off the line, and on average, 0.008 or 0.8% are defective. How many would we expect to see? How would you calculate that? Again, if you didn't know any of this stuff we've been talking about today, you would get the right answer. What would you just do? Wouldn't you just multiply them? You'd be like, well, if 2% of people have, you know, like whatever color eyes or something like that, and there were 150 people, I would just be like, let's multiply them, because that's how many I expect to get. So that's the expected value, and we'll see what the variance is after we answer Brandon's question. Come again? How come there's a what? 0.8%, so the probability is 0.008. I know, trying to confuse you. It's 0.8%. That's right, I think that Sam and Grace will straighten you out. Okay, good. You're good? All right, so the expected value, not just for this binomial distribution, but for any binomial distribution, is just the two parameters multiplied together. We want to make sure, I want to make sure we're clear again here. Any binomial distribution is completely known. I can make that whole table if you just tell me what n and p are, right? I know how to make the table. And I know how to compute the expected value. And I also know how to compute the variance. It's npq, you could say. Or np times 1 minus b. This one, I have a very good intuition on why that's true because we just talked about it. This one I can prove, both of these are provable from the definition of expected value and the definition of variance and the definition of the binomial distribution. All of these you can prove, and I've done that before. But I don't have like a great feeling as to why this is true necessarily. I don't know if someone else has some intuition about why that's true. We can prove it's true algebraically. This one, even if I didn't do the algebra, I would kind of guess that that was the expected value. But I'm not so sure about the variance. Maybe we just need to know it. I don't know. But you can derive it from first principles. Anyway. Think about why. Maybe I can come around some intuition on that, but it's hard. Okay. Regardless, it's not hard to calculate. So for the last example, let's return to the same exact problem with the widgets. We already calculated, or we said at least how we were going to calculate the expected value. So let's calculate both of these for the last problem. And maybe arrow, you can get this on those two when you get it. Those two values. Yeah, same question. Whenever you're ready. What'd you get for the expected value arrow?
1.2.
And the variance?
Let's calculate it yet. I'm just trying to see if it goes.
Oh, you're not allowed to do that. No, we got arrow. She's all over it.
Here, 1.1904. 1. Yeah.
Yeah, you write it down right? Okay. Good. And by the way, this is in widgets for the expected value, 1.2 widgets. Which again, we want to make sure that we're clear. There's never a time on a given morning that when you do this, you pull 150 off the line, that you'll get 1.2 detected widgets, right? But what we're saying again, we want to emphasize the thought here about expected value. If you do this every morning, pull 150 widgets off the line and check. In the long run, on average, you will get 1.2 per day. Yeah.
Or if they were to, or would there ever be like a way to rephrase the question which would have to round it one digit?
Not for expected value.
So you can't really have a fifth of the widget be expected.
Right. I mean, you can have that as an expected value. We don't have the demand that expected value be an integer or evaluate the distribution involved. Yeah. But I hear what you're saying. Yeah. That's the variance that we computed yesterday. So the other way you can compute it would be by hand. So well, let's answer that in a couple ways. The first answer is from Friday, we said you could calculate it using don't forget this formula. Just actually like build your table of 151 values and their probabilities. And for each value, subtract the mean, which is this, square it, multiply by the probability, and then sum them all, and this is what you'll get. Now, the next question is, so that's like the technical definition of variance, right? So now you can compute variance for every discrete distribution you'll ever see in your life. Good, yay. Now, it still remains to be seen, like, why would you do that? What is it useful and what does it say? And the way that we describe that is like, in general, it's the average squared distance you are from the mean, which so it gives a sense of spread of the data. So if this is a big number, it means the data is more spread out. The distribution, the values of the distribution. And if it's a small number, it means all the distribution, all the probabilities, all the values really close. And so, and if you want the standard deviation, which is in widgets, not widgets squared, you can take the square root if you like. Okay. All right, more practice. Here's Alex, who is ridiculously good at basketball. Like better than like NBA historical averages. But let's just go with it for the sake of the problem. All he does is do free throws all day. Okay. Practice. Practice. Sheet. Big sheet. Oh, sheet. He. That's my right gesture. These are not meant to be different than the last one. I'm actually going to try and make another point with this in a second. So just compute them really quickly, and I will call on 3 people who will not give me the work, but will just give me an answer on each of these. Okay. So just be ready with an answer for each of these. We'll give.
Oh, so we can't keep it in exact form.
Well, you can, however you like. Whatever. We just want to kind of just check in and make sure you're getting right answers. Is all. Hopefully everyone's doing well on this now. This is your opportunity to practice. First one. You ready? Grace. You ready? And you're going to be on for I'll call on you.
Oh, that's let me check. Oh, 20. That is 190. Oh, that's right.
Use the full value from the previous one. Yeah, always. All right, let's start getting some of these answers up.
Okay. So I have 0.8 to the 20th, which is 0.0115.
Point zero.
0.01153.
3 sig figs, is that look good? Someone else confirm? Well, if it doesn't say, then we'll do 3 sig figs. I know, because it's different in other classes.
Yeah.
Right. Yeah.
I have a question. So for 3 sig figs, would 0.01 be 3 sig figs, or would it have to be 0.01?
This is 3 sig figs.
Oh, this is 3 sig figs.
We don't count. We don't count the zeros.
Oh, we don't count the zeros. Sorry.
Unless they're in the middle of the number.
Oh, unless they're in the middle.
Yeah.
Okay.
Grace, B? What's the final answer here? Confirm on that?
Yes.
Can you just give me a final answer on this one? When you're ready.
0.1773.
0.17?
Yeah. Or 1.8.
17.
1773 or 1779.
We'll do 3 sig figs on that too. Can someone confirm that too? That's a little bit more of a calculation, right? You had to calculate probability of 18 plus the probability of 19 plus the probability of 20 and add them up. Anyone can confirm that? Besides Kate? Do you? Did you actually do this?
Can I agree with Kate?
Really? Katie, for real? Okay, great. Well, let's take this opportunity now to also share with you a calculator feature that we've been holding out on for you a little bit. Now, actually, most of these are calculated pretty quickly, but even without. It's not too bad, right, what we've been doing? On the calculator, you'll want to access the distribution menu, D-I-S-T-R. And you can hit that by going to second bars. You see it right there? And one of them right away looks like the one you might want here. And that's Binom. We're going to introduce PDF first here for those who know these things. Binomcdf, which is a good name for this. We're talking here about the binomial probability distribution function, okay? And the syntax is n, the number of trials, p, the probability of a success, and then x, the trial that we care about. So try this on B, for example. by typing in, see if you don't get 0.137 when you type in Binomcdf. Well, hold up. I'm only talking about B right now. And we need to type in, oh, you mean in general. You think C is just wrong.
Yeah.
After Caden and then Dean, you gonna confirm? Or? Huh? I'm never trusting you guys. All right, let's go back to B now. So B can be computed in the way that we've been talking about today. But your calculator has this coded in, so if you want to use it, you can. If you type in 20, what are we looking for? 18, or 0.8 and then 18, you should get 0.137 from your calculator. That's the command there from the Binomcdf function.
Wait, Mr. Chase, if you don't put in an x value, will this do anything?
If what?
If you don't put in an x value, like...
No, it will require that you have all three of these
So if
things.
you want to do like all 20, just put 20, 0.8 and 20 right?
You want all 20 of, all 21 of them? Wait, what?
No, if you want all 20, if you put for A, how would you do A? How would you calculate A?
Oh, you can put 20 in here, sure.
Oh, okay, cool.
I think that's certainly overkill. This is already a little overkill, given that this calculation wasn't very hard to do without the command. But there you have it, and we'll need something. We'll need the other one on in a second too. So we'll introduce the syntax now. Yeah, well, let's actually show one where it really makes sense to use the CDF function, because that's where the power is going to lie. So we need to say what that's about. 3. Yeah, we're gonna do. Yeah, we're gonna. All right, so here's an example. Already, you're thinking, well, I don't know. We don't necessarily need those commands, but I can see that this is getting a little laborious to do this by hand or to type it all into the calculator. All these different commands. So here's one that I think we're definitely gonna need the calculator on as we do the second part. So I don't know where this number comes from. I would guess that it's higher than that actually, but so 33%. 33% of drivers text or read texts while driving. Let's assume that that's true, including in the sample we've just taken of 300 US drivers. So find the probability for, first of all, that A happens, that we get 90. So we've got a binomial random variable. We're selecting 300. We're going to be testing 300 people. And 33% is the probability that a given person has text while driving. So we want to calculate here the probability of our random variable taking on the value exactly 90. So let's actually write out both ways of doing this. Write with the calculator command, but also with the actual method we've been using here. So when you're ready, Ashley, if you're willing to give us what the form of the calculation would be, not using the calculator command, but how would that go? Good. Oh, sorry, did you say that? Or you can type in the calculator, binom, just like we've been doing, PDF, 300, comma, 0.33, comma, 90. And in either case, you'll get an answer that works for us. And in the part B that I put up here, it says, what's the probability that at least 90 say they text and drive? We're asking for what inequality to be here? We need x to be what?
Greater or equal.
Yeah, by at least we need to do some English on this. But by at least 90, we mean 90, or anything greater than that, right? So we're looking for this probability. So if you were to look at this whole distribution and kind of graph it as a histogram or something like that, you can imagine the tails here too, that the distribution would look something like that, right? And we're looking for 90 in part A, just that probability. But in part B, we're looking for all of these probabilities summed up from 90, including 90, and all above that. Okay, all the way up above that. That's the probability we seek in part B. Now there is another calculator feature that you've been looking at, and that's the Binomcdf feature. And that always calculates the probability for any cumulative distribution. This is a C stands for cumulative, which is a good name for it. That always calculates the probability of x less than or equal to little x. So NPX is the syntax, and what it interprets it always as is not the thing we want, unfortunately, but always the value we're at and everything lower than it. So it always calculates, if you've got a little distribution here, it always calculates your value and to the left. Your value, including your value, and to the left. That's just always what we mean by a cumulative distribution function. Just know that, and we'll do more with cumulative distribution functions in the next unit too. But in order to do that, then we need to kind of retool our problem. What do we need to calculate that instead? Yeah, 1 minus some probability. Let's see if we can say it right. The probability of x. We need to have it in terms of this Binomcdf feature on the calculator. It needs it to be less than or equal to 89. It's very easy as you're doing your homework problems to be like off by 1 somehow because you have misinterpreted the question. You're like, you think this should be a 90. Like, just be careful. Speak English to yourself. Be like, okay, what are the ones that don't count? 89 and below, right? So just say that to yourself. And then finally, we can actually cite, actually type this in your calculator and see how you do. Get this actually for us right now. 1 minus Binomcdf on your calculator. 300.33, comma 89. And give us an answer on that. It says homework 9 on it. It should say homework 11 on it. Just whatever. This is the last homework we had for this series. You don't need to. I mean, the way I have it written there, 1 minus probably less than or equal
History in here. Is this homework? You did. Oh, it takes us 3 forever. I don't know.
All right, what's the answer up here? 7-9. 879. 879. And we didn't say what this one was. What'd you get here? Anyone remember? Nobody cares. All right, see ya.